5.1 Area and Estimating with Finite Sums. The outline of this video is as follows. We will discuss several key topics. We will begin by learning how to approximate the area under a curve using finite sums. We will then define specific methods for this, known as upper sums, lower sums, and the midpoint rule. After that, we will apply this same summation technique to estimate the distance traveled by an object based on its velocity. This will lead us to an important distinction between an object's displacement and the total distance it has traveled. Finally, we will see how this method allows us to approximate the average value of a continuous function over an interval. This section introduces a powerful method for approximating complex quantities. The core idea is that we can calculate things like area or distance traveled by breaking the problem into many small, simple pieces. We first approximate the quantity for each individual piece, and then we sum all of those small contributions together to get a total estimate. For example, we might use tiny rectangles to estimate a large, curved area. This process of approximation using finite sums is the conceptual foundation for integration, which we formalize by seeing what happens as these pieces get smaller and more numerous. Let us focus on a specific problem: how to find the area of a region with a curved boundary. We want to find the area of the shaded region R, which is shown in the figure. This region lies under the curve y equals 1 minus x squared, above the x-axis, and is bounded on the sides by x equals 0 and x equals 1. The challenge here is that there is no simple geometric formula for a shape like this. We will have to approximate this area using simpler shapes, like rectangles, which we can easily measure. Our first approximation method is called an upper sum, which uses rectangles that completely contain the region R. To do this, the height of each rectangle is set to be the maximum value the function reaches within that rectangle's base. For our function, y equals 1 minus x squared, which is decreasing, this maximum value is always found at the left endpoint of each interval. As you can see with two rectangles, this method clearly overestimates the area. The calculation gives 0.875. Using four rectangles gives a better estimate of 0.78125, but it is still an overestimation. To complement the upper sum, we now use a lower sum. This method uses rectangles that are contained entirely inside the region R. This time, the height of each rectangle is determined by the minimum function value within its interval. For our decreasing function, this minimum value occurs at the right endpoint of each interval. Using four rectangles, we get a total area of approximately 0.53125. This is called a lower sum because it clearly underestimates the true area. The key benefit is that we now have bounds. We know the true area must be somewhere between 0.53125 and the upper sum of 0.78125. A third method for estimating the area is called the midpoint rule. This approach often provides a more accurate estimate than the upper or lower sums. Here, the height of each rectangle is the value of the function f at the midpoint of its base. For example, with four rectangles on the interval from 0 to 1, the midpoints we use are 1 divided by 8, 3 divided by 8, 5 divided by 8, and 7 divided by 8. This gives an area estimate of approximately 0.671875. The midpoint rule is effective because the small areas where the rectangle is over the curve and the areas where it is under the curve tend to partially cancel each other out. All three methods we have seen are just different ways of constructing a finite sum. They all follow the general form. We sum up terms, where each term is the function evaluated at a chosen point, c sub k, multiplied by the width of the rectangle, delta x. The key idea is that as we take more and more rectangles, increasing indents, our approximations get better. The width of each rectangle gets thinner, and the error from our over or underestimates gets smaller. As shown in Table 5.1 from the textbook, As n increases, the lower, upper, and midpoint sums all converge toward a single value. This limiting value is the exact area, which for this problem is 2 divided by 3. Now let us apply this same summation idea to a different problem. Calculating distance. Our goal is to find the distance an object travels from time t equals a to t equals b, given its velocity function v of t. If the velocity were constant, we would just multiply velocity by time. But if the velocity is changing, we can adapt our area method. We subdivide the time interval into many short time intervals, which we call delta AE. We assume that during each tiny time interval, the velocity is fairly constant. We can then estimate the distance traveled in that short time by multiplying the velocity at a chosen point, v of t sub k, by the time interval delta t. The total distance is then approximated by summing up all these small individual distances. Let us work through an example of estimating distance. A projectile's velocity is given by the function f of t equals 160 minus 9.8 t in meters per second. We want to find how far it rises in the first 3 seconds. Since this velocity function is decreasing, using the left endpoints for our time intervals will give an upper sum, and using the right endpoints will give a lower sum. If we use 3 subintervals, each with a width delta t of 1 second, our upper sum is 450.6 meters. Our lower sum is 421.2 meters. The true value, 435.9 meters, lies between these two estimates. Just like with area, using more, shorter intervals would give us a more accurate approximation. We must be very careful about a crucial distinction: the difference between displacement and total distance. If an object reverses direction, its velocity will change sign. If we simply sum the velocity, v of t times delta t, the negative velocity will cancel out the positive velocity. This sum estimates the object's displacement, which is its net change in position, or s of b minus s of a. However, if we want to know the total distance traveled, we must use the object's speed, which is the absolute value of its velocity. To find total distance, we must sum the absolute value of v of t sub k times delta t. This way, all motion counts positively. This example makes the distinction between displacement and distance clear. A rock's velocity is given by v of t equals 160 minus 32 t's in feet per second. Notice that the velocity is positive for the first 5 seconds as the rock rises, but it becomes negative after 5 seconds as the rock falls. If we sum v of t over 8 seconds, we are estimating the rock's displacement. At 8 seconds, it is at a height of 256 feet, so that is what the sum will approach. But to find the total distance traveled, we must sum the absolute value of v of t. The rock traveled 400 feet up and then fell 144 feet down. Therefore, the total distance traveled is 544 feet. Summing the speed gives this total path. Our summation technique has another powerful application: finding the average value of a continuous function on an interval. This is not as simple as averaging a few numbers, because a continuous function has infinitely many values. For a constant function, f of x equals c, the average is just c. We can think of this geometrically. The average value is the height of a rectangle that has the same area as the area under the graph. We can extend this idea to any function. Imagine the area under the graph is a volume of water. The average value is the height the water would settle to. Therefore, we define the average value of a function as the area under its graph, divided by the width of the interval, b minus a. Let us apply this new definition to estimate the average value of the function f of x equals sin of x on the interval from 0 to pi. First, we need to find the area under this curve. We can approximate this area using our finite sum methods. For instance, using an upper sum with 8 rectangles gives an estimated area of about 2.364. Second, we divide this estimated area by the length of the interval, which is pi. This gives an average value approximation of 2.364 divided by pi, which is about 0.753. Since we used an upper sum, this estimate is higher than the true value. The exact average value, which we will be able to find later, is 2 divided by pi. Let us summarize the main concept of this section. We have seen how 3 different seeming problems, finding the area under a graph, the distance traveled by an object, and the average value of a function can all be approximated by the same method. This method is the finite sum. The process involves subdividing an interval from a to b into n subintervals, each of width delta x. In each subinterval, we choose a point c-sub-k and evaluate the function there. The approximating sum is the sum of these values, f of c-sub k, each multiplied by the width delta x. We know the true value lies between the upper and lower sums, and all our approximations get better as we use more and more rectangles. To review, let us consider a couple of questions. First, if you have a function that is positive and decreasing on an interval, what points would you choose in each subinterval to get a lower sum? What points would you choose to get an upper sum? Second, imagine an object's velocity is positive from t equals 0 to 10, but negative from t equals 10 to 20. If you sum the velocity v of t sub k times delta t over the whole interval, what physical quantity are you approximating? And what sum would you use if you wanted to find the total distance the object traveled? Thinking about these will solidify the key concepts.